Let us continue coordination compounds. In the coordination compounds, we have discussed valence bond theory. Using valence bond theory, we said hybridization, shape of the complex, then experimental magnetic nature we have explained, then geometrical isomerism, optical isomerism we have explained. Then, if we do not know the magnetic moment from the experimental analysis, can we explain the hybridization of coordination compounds? No. Then magnetic moment of the complex is how much? Quantitatively, valence bond theory is not explaining. Valence bond theory, what it does, it takes magnetic moment from experimental data, and as per that, it forcing the electrons to pair up or not forcing the electrons to pair up, it says. Therefore, this valence bond theory is not explaining magnetic moment quantitatively. Regarding color of complexes, valence bond theory, I have not said anything. Then stability of complexes also, it did not say. Then it did not say about ligands, whether the ligands is weak field ligands or strong field ligands. Regarding ligands also, valence bond theory did not say. So what are the limitations of valence bond theory means? Valence bond theory, I have not explained the magnetic moment quantitatively, color of complex, stability of complex, ligand strength. These and all not explained by valence bond theory. Therefore, another theory introduced, that is called what means crystal field theory. Crystal field theory is introduced. Crystal field theory. Now, in the crystal field theory, how it is there means, crystal field theory considers central metal and ligand. Between central metal and ligand, what is there means electrostatic force of attraction is there. Electrostatic force of attraction. So, crystal field theory says that between central metal and ligand, what is there means electrostatic force of attraction. Crystal field theory considers metal ligand interaction is electrostatic force of attraction. But valence bond theory considers coordinate covalent bond. Valence bond theory considers between metal and ligand what type of interaction means a dative bond, coordinate covalent bond. But crystal field theory considers between metal and ligand electrostatic force of attraction is the interaction. Sir, why valence bond? Why like crystal field theory said like this? Crystal field theory says that central metal is having positive oxidation number. Positive oxidation number. Ligand, anionic ligand is there. Anionic ligand. Between them, electrostatic force of attraction, like that it considers. Suppose ligand is neutral ligand. Ligand is neutral ligand. Then consider dipole of ligand. Consider ligand as a dipole. Negative pole of dipole attracting this positive charge of metal. Like that it considers electrostatic force of attraction. So as per a crystal field theory, between central metal and ligand, electrostatic force of attraction. That is the main point of crystal field theory. Based on that, based on this point, based on electrostatic force of attraction, it explains complexes. Complexes in the sense the ligand's strength, stability of complexes, color of complexes, then magnetic moment of complexes. About complexes, crystal field theory explains. For that, it considers main point is what means electrostatic force of interaction between central metal and ligand. That's what it considers. Sir, it considers either attraction or repulsion in the sense which it is considering. That we will consider later. Okay. Now we will see in the central metal, valence shell contains d orbitals. How the energy of d orbitals will be there? The energy of d orbitals depends on which factors? That we will see now. Now we will see isolated gaseous free metal we will take. Isolated gaseous free metal will take. Isolated in the sense between metal atoms there is no interaction. Gas means free metal means in the gaseous state only isolation is possible. That means we have taken metal in the gaseous state in which metal atoms are isolated. Now in the metal, valence shell will be there. The valence shell has 5d orbitals. That 5d orbitals will take. One is dxy, next one is dyz, next one is dxz, next one is dx square minus y square, next one is dz square. So 5d orbitals present in the valence shell of metal. How these 5d orbitals will be there? Their energy will be same. Therefore, they are degenerate. They are degenerate. Okay. So, in the isolated gaseous free metal, the valence shell contains 5d orbitals. All the 5d orbitals have equal energy. Therefore, the d orbitals are degenerate, we are saying. Next, we will take the metal to the external field now. We are taking the metal to the external field. What is the external field? External field is the spherical. External field is the spherical, symmetric, negative charge. It is the external field. External field is what means spherical, symmetric, negative charge. It is the external field. So and so field is given to each d orbital in the valence shell of free metal. So and so spherical, symmetric, negative charge. So and so external field is given to each d orbital in the valence shell of metal. Okay. Now what will happen? It is negative charge. This d orbital contains electrons. Electrons have negative charge. Between these electrons and this negative charge, there is a repulsion. Because of repulsion, this d orbital's energy will be more here, more in this place. Okay. So now we are considering d orbitals in the isolated gaseous free metal atom. It is isolated gaseous free metal atom. Okay. In the isolated gaseous free metal atom, all the 5d orbitals have equal energy. Okay. All the 5d orbitals have equal energy in the isolated gaseous free metal atom. Now, it is taken to external field. External field is having negative charge. Now, this is taken to external field. External field is having negative charge. How this external field is given to each d orbital, that means theoretically we are imagining this concept. Okay, practically it is not possible. Theoretically we are imagining. We are giving for each d orbital spherical, symmetric, negative charge as external field. Therefore, here electrons, here negative charge go for repulsion. Therefore, this energy getting raised. So now energy is raised. Now energy is raised. Okay. So energy is raised now, we are saying. Sorry. How the energy of 5d orbitals will be there at the present situation? At this situation, how the energy of these 5d orbitals will be there? Energy of these, will they be equal or unequal? That means for each d orbital, we have given imaginary external field. How the external field is there? Uniformly is there with respect to each d orbital. Therefore, all the d orbitals will have high energy but equal. Therefore, now we got degenerate 5d orbitals. Degenerate 5d orbitals we got. All the 5d orbitals have equal energy. Therefore, these 5d orbitals have equal energy. Therefore, we are saying these are degenerate, we are saying. Degenerate d orbitals, like that we are saying. Next. Actually, how it will be there? Now we will see practically. Practically how it will be there, like that we will talk. Because like this is imaginary. This is imaginary. This one is imaginary. Why it is imaginary? Because all the 5d orbitals are not having uniform shape. Dx square minus y square, dx z square are different structures. But dxy, dyz, dz, xz same. But these three different from these two, no? When the structures are different, when the shapes are different, how can we give spherical, symmetric, negative field, negative charge, uniform field? How to give? It is not possible, isn't it? Therefore, it is imaginary only. So what is practical? Practical says, practically, how the 5d orbitals will be there in the central metal, in the valence shell of the complex. So we are taking a complex. In the complex, you can see different complexes has different central metals. Therefore, if nature of central metal is different, then the valence shell 5d orbitals will have different energies. Therefore, in the central metal, valence shell has 5d orbitals. That energy depends on what? Nature of central metal. Whether central metal is cobalt or iron or nickel, which is central metal, based on that, energy of d orbitals will be varied. Next, nature of ligand. Ligand is interacting with the central metal. Between ligand and central metal, interaction is there. Due to interaction, d orbitals, valence shell d orbitals of central metal, energy will become different. Then, geometry of complex. Octahedral complex, square planar complex, tetrahedral complex, like that many complexes are there. Many shapes are there for complexes. Many coordination numbers are there. Due to difference in geometry, the d orbital's energy also will be different. So, now we will see how the d orbital's energy will be there based on these factors that we will see. Now we will take central metal. We are taking central metal. In the central metal, valence shell we will take valence shell d orbitals we will take dxy, dyz, dzx, dx square minus y square, dz square. 5d orbitals we will take. Then ligand we will take. Ligand. This ligand is approaching central metal in order to form complex. So ligand is having electron cloud. This d orbital is having electron cloud. Between them, repulsion is possible. Between this d orbital of valence shell of central metal and ligand electron cloud, repulsion is possible. Now, this ligand is repelling even this d orbital also. Do you think that magnitude of repulsion between these two and these two will be same? No. Why? This shape and this shape, this orientation and this orientation, if you see, that is different. Suppose we are taking octahedral complex. Octahedral complex. We will take central metal. Central metal we have taken. Ligand approaching this central metal. Ligand approaching the central metal in x-axis, y-axis and z-axis. X-axis, it is y-axis, it is z-axis. In this axis, ligand is approaching. Ligand approaching in this axis. Now, central metal valence shell is having d orbital. How that d orbital will be there? That we will see. Now we will write d xy orbital. We will write dxy orbital like this. Dxy orbital means that is in between x and y axis, isn't it? Now see this lobe in between x axis and y axis. It is dxy. But dx square minus y square, how it will be there, you see? Dx square minus y square means that lobe is along x axis and along y axis. Correct? So now see, ligand is approaching along x axis and y axis, no? Now say that ligand and this d orbital getting repulsion, no? This d orbital electron, ligand electron, between them repulsion is possible. Now do you say repulsion between these two and repulsion between these two is same? Therefore we can say between these two repulsion is different. So how that magnitude will be there, which is having higher magnitude of repulsion, in which magnitude of repulsion is low, that we'll see. Now in the octahedral complex we have taken. Now we will take dxy orbital from central metal. It is what, in the sense we will write dxy orbital. In dxy orbital 4 lobes are there. Those 4 lobes I will write like this. Now I will mention x-axis, y-axis. Now this is x-axis, this is y-axis. See, remember that dxy orbital means lobe will be in between x and y-axis, correct? So ligand approach will be in x-axis and y-axis. Ligand will approach along x-axis and along y-axis in the octahedral complex. Now see, d orbital lobe in dxy is in between ligands in the central metal. Now we will take dx square minus y square orbital. Okay, so central metal dx square minus y square orbital will take. It is a dx square minus y square orbital. Now we will say xy axis, will say it is the x-axis, now x-axis will be like this. Y-axis will be like this. So you see x-axis and you see y-axis. Ligand is approaching along x-axis and along y-axis. Now you see this d orbital lobe and the ligand repulsion is there. Here also this d orbital lobe and the ligand repulsion is there. Do you think that repulsion between this ligand and d orbital lobe here and here same? Certainly no, because both are approaching with each other directly. Here both are not approaching directly. Therefore here repulsion will be more, here repulsion will be less. Okay, therefore we can say between ligand and this d orbital repulsion magnitude is less, between them repulsion magnitude is more if you take octahedral complex. Suppose if you take tetrahedral complex, this may different, this may vary. Tetrahedral in the sense ligand's approach to the central metal is different from octahedral. Square planar means that is different from tetrahedral, like this is there. Okay, so based on geometry the repulsion magnitude will vary. Don't think that this repulsion magnitude always like this. Okay, for octahedral we have considered like this. So therefore this dxy and dyz dzx, how it will be there means they will have uniform repulsion with ligand. Dxy, dyz, dzx will have uniform repulsion with the ligand. Why? Because dxy, how it is there, like that only dyz and dzx will be there, only axis will be different. Therefore dxy, dyz, dzx will get a uniform repulsion from ligand. dx square minus y square will get a higher magnitude of repulsion from ligand in octahedral complex. What about dz square? That we'll see. Dz square, how it will be there, that point we'll see. Dz square, here I am writing 2 lobes in the z axis. In the z axis I am writing 2 lobes. Now I am giving a z axis, I am giving, I have given a which axis, in the sense z axis I have given. Okay, z axis. Then I will write a xy plane. Now I will write xy plane. Now in the xy plane I have written electron cloud. It is in which one? In the sense xy plane. In the xy plane, dz square orbital electron cloud will be there. This is what in the sense dz square orbital. Now ligands approach we will see. Ligands approach along x-axis, y-axis and z-axis. No, along z-axis ligand is approaching. Therefore, how the repulsion between ligand and dz square will be there? How the repulsion will be there? This repulsion magnitude will be higher than this one. Ligand dz square orbital, between them repulsion is possible. This magnitude will be greater than that of this magnitude. And how these two magnitudes will be there? These two magnitudes also will be different, because see the dx square minus y square orbital and the dz square orbital, their shapes are different. No, therefore certainly these two will get different magnitude of repulsion from ligand. But we are considering, we are assuming that these two repulsions are same. We are assuming, okay, we are assuming these two repulsions are same. Therefore these two will have same energy, okay, as per assumption. So as per assumption, these two will have same energy, these three will have same energy. This is one set, it is another set. This set is having lower energy, this set is having higher energy. This set we are calling as EG set, this set we are calling as T2G set. Spectrochemical words these are. Spectrochemically this is designated as EG set, it is denoted as T2G set. So how these energies will be there, that we will see. Now that T2G energy will be lesser than this one. The T2G energy will be lesser than this energy. This T2G contains which orbitals in the sense dxy, dyz, dzx. Then EG set is having energy greater than this. EG set is having energy greater than this. EG set is having orbitals dx square minus y square, dz square. EG set is having these two orbitals. T2G set is having these three d orbitals. Now, energy difference between this EG set and T2G set is called crystal field splitting energy in octahedral complex. If you take tetrahedral, you have to say tetrahedral. Here we have considered octahedral, therefore delta naught we are saying. Delta is called what? Crystal field splitting. Why splitting? Because the 5 d orbitals energy has got split into two sets, therefore splitting. Why crystal field? In the crystal only like this splitting takes place. No, which crystal? Complex crystal. In the complex crystal like this splitting takes place, therefore we are saying it is called, delta is called crystal field splitting. O is called octahedral. So this delta naught is called crystal field splitting energy. That means energy difference between T2G and EG, like that you can say. Now this energy is called barycenter. That energy is called what? Means barycenter. Okay. Now T2G energy is lower from barycenter by 0.4 delta naught. T2G energy is lower from barycenter by 0.4 delta naught. EG energy is higher from barycenter by how much? Means 0.6 delta naught. EG set energy is higher from barycenter by 0.6 delta naught. T2G energy is lower from barycenter by 0.4 delta naught. Okay, so like this d orbitals energy will be there in the octahedral complex. In the octahedral complex, d orbitals energy will be like this. It is said by crystal field theory. Crystal field theory says like this based on interaction between ligand and central metal d orbitals. Okay. So crystal field theory says crystal field splitting energy, it says. Why it said like this? In order to explain color of complexes, magnetic nature of complexes. Okay, then ligand, in order to explain about complexes, experimental facts about complexes. For that case only crystal field theory explained this one. Sir, now we will see this crystal field splitting energy, this delta naught depends on what factors? This delta naught depends on what factors, that we will see. Okay, now we will take some complexes, that is CO NH3 6 times 3 plus. This complex we will take. For this complex we will see delta naught. We are taking delta naught. Delta naught how much means 296 kilojoule per mole. Next we will take rhodium complex. Rhodium NH3 6 times 3 plus. For that delta naught is how much means 406. Next we will take iridium complex. Iridium complex we will take. For that delta naught is 490 kilojoule per mole. Okay, we have taken delta naught like this we have taken. Now here ligand is same, coordination number is same, shape is octahedral, shape also same. Only thing what happens, down the group size of central metal increases. Down the group size of central metal what happens means central metal increases. Here cobalt, rhodium, iridium, one group, cobalt family. Down the group size of central metal increases. How the delta naught increases? How to explain this? Size of central metal increases. Therefore, valence shell d orbital and ligand distance decreases. Therefore, interaction increases. Therefore, crystal field splitting energy increases. Okay. Next, we will see. We will change the ligand and we will see crystal field splitting energy. Now we will take the complex Fe H2O 6 times 2 plus complex we will take delta naught in terms of wave number. Therefore, per centimeter unit is given. Now value is crystal field splitting energy is 10,400 per centimeter. We will take another crystal Fe Cn 6 times 4 minus. Here delta naught is 32,850 per centimeter. Now here central metal is Fe, here also Fe, here oxidation number is +2, here also +2. Ligand is different, crystal field splitting energy is different. Here crystal field splitting energy is high because ligand strength is high. Crystal field splitting energy is low because ligand strength is low. This ligand strength is high, therefore it is repelling to higher extent with the d orbitals when compared to this. Therefore here crystal field splitting energy is high, we are saying. Okay, so if crystal field splitting energy is high, then ligand strength will be high, we are saying. So based on crystal field splitting energy, ligand's strength will be determined. That ligand strength will be said in a order. That order is called a spectrochemical series. That order we will see. That order is I minus less than, Br minus less than, Scn minus less than, Cl minus less than, sulfide less than, fluoride less than, hydroxide less than, oxalate less than, water less than, isothiocyanate less than, EDTA less than, ammonia less than, En ethylene diamine less than, cyanide less than, carbon monoxide. Okay, like this we have given. We have given ligand field strength, we have given. It is called a spectrochemical series. Now see, ligand field strength, how we said? Crystal field splitting energy is high means ligand has higher strength, we said. Crystal field splitting energy we are saying based on repulsion between central metal d orbital and ligand, isn't it? Now you see here, Cn minus is anionic ligand, CO is neutral ligand. For this net charge is 0. For both the number of electrons same, they are isoelectronic species. Now you take Cn minus and CO. It is a neutral ligon. It is anionic ligon. It is anionic ligon. Now you take central metal d orbital. D orbital you take central metal d orbital. Between these two repulsion is possible. Between these two also repulsion is possible. But how the repulsion will be there? Do you think same? Here only high, here only low, isn't it? Because it is neutral, whereas it is anion. Therefore, here magnitude of repulsion is more when compared to this one. Therefore, how the crystal field splitting energy should be there? For this more, for this less, isn't it? But how it is there? Like this is there. CO is having more when compared to Cn minus. Crystal field splitting, crystal field theory unable to explain this fact. Therefore, crystal field theory also is having some limitation, but though limitation is there, it explains about something. Sorry, even valency bond theory is there. Using valency bond theory only, we said complex shapes. Coordination number 6 means we are saying octahedral, because valency bond theory says between metal and ligand, dative bond is there. Dative bond means directional nature. Based on directional nature only, we are able to say shape. But using crystal field theory, we cannot say shape of the complex, because crystal field theory considers electrostatic force of interaction. Electrostatic force of interaction do not have direction. Then how to say shape of complex using crystal field theory? Therefore, to explain complexes, many theories are there. Another theory called the ligand field theory. Like that, many theories are there. Each and every theory is having certain limitation. And each and every theory is explaining certain experimental facts about complexes. Therefore, we have to consider all the theories. What are the merits, what are the demerits, everything we have to consider and we have to correlate. That's all. So we said now ligand field strength, we said it is called order of strength of ligands. This series is called a spectrochemical series. Okay. Now how to go for electronic configuration, that we'll see. Electronic configuration of central metal valence shell d orbital in the complexes, that we'll see. Now we are going for electronic configuration of valence shell d subshell central metal in the complex. Okay. Now we will consider octahedral complexes. In the valence shell central metal is having D1 configuration. This valence shell central metal D subshell is having two sets. One is called T2G set, another one is called EG set. Now, if the central metal valence shell is having one electron in d orbital, that electron will go to where in the sense T2G. Therefore, the electronic configuration is what means T2G1 EG0. Okay, it is a central metal valence shell d subshell electronic configuration in the octahedral complex. Okay, if central metal valence shell is having D2, then we can say T2G2 EG0. How T2G2 we said D2 means we will say T2G like this. Here one electron, here one electron. EG is not having electrons. Okay. Now we will take D3. How to say D3? Now T2G, EG we are taking. This is what means T2G, it is what means EG. Now D is having 3 electrons. One electron here, second electron here, third electron here. This we can write it as T2G3, EG0. Okay, D3 we can write like this. Next we will write D4. Now if central metal valence shell is having D4 electrons, then how to write configuration? That we will write. Now we will take T2G and EG. T2G and EG we have written 4 electrons, one electron here, second electron here, third electron here, fourth electron. Shall we pair with T2G or shall we go for EG? Two sets possible. One is pairing in EG, T2G. Another one is what in the sense going to EG. That is another possibility. So 4 electrons, 1 year, second year, third year, fourth electron going to Eg. This is another possibility. Now, under which condition which is possible? Under which condition which is possible, that we will see. Now, here this difference is called delta naught. Delta naught and pairing energy. If delta naught is less than pairing energy, and another possibility, delta naught is greater than pairing energy. It is another possibility. Okay. One we said delta naught is less than pairing energy. Another we said delta naught is greater than pairing energy. What is pairing energy? Pairing energy means what? Now, we'll consider here fourth electron. Here fourth electron. This fourth electron goes to this place for pairing. While fourth electron goes here for pairing, this electron will repel that electron, isn't it? If that electron overcomes this repulsion, then that electron can come and pair here. Otherwise, cannot. So, to overcome that repulsion, how much energy is required? That energy is called pairing energy. So, what is pairing energy? This electron coming for pairing here, while this red electron is repelled by black electron. That repulsion, if it is overcome, then only red electron can come to black electron. So, how much energy is required to overcome repulsion between them? That energy is called a pairing energy, we can say. Sir, what is crystal field splitting energy? Delta naught means energy difference between T2G and Eg. Now, if pairing energy is less and delta naught is more, then fourth electron will go for pairing. If pairing energy is more and delta naught is less, delta naught means energy difference between Eg and T2G. If pairing energy is more, delta naught is less, then fourth electron won't go for pairing, it will go to Eg. Fourth electron will go where? It will go to Eg, it is not going for pairing. So when pairing takes place, when pairing not takes place, that depends on delta naught and P, we said. Now we will take. We have discussed two complexes we have discussed in valency bond theory. One is called what means COF6 3-. We said the experimental fact says that here 4 unpaired electrons. Here 4 unpaired electrons, we said. In the COF6 3-, we said number of unpaired electrons 4. That is experimental fact said. Another complex we have discussed, CONH3 6 times 3 plus. Experimental analysis said that here unpaired electrons 0. Unpaired electrons 0. Why is it so? That is not explained by valence bond theory. How crystal field theory is interrupting these points, that we'll see. Now, delta naught. Delta naught is how much in the sense? Delta naught is 13,000 year per centimeter. In terms of wave number, it is said. For this complex, 23,000 per centimeter. Delta naught. Pairing energy. Pairing energy is 21,000 per centimeter. Pairing energy here also same, because pairing means with another electron only, no. So pairing energy is like this. Now you see COF6 3-. Delta naught and pairing energy you see for COF6 3-. Delta naught is less, pairing energy is high. Therefore, how here configuration will be there and how here configuration will be there, that we'll see. Here central metal is what means cobalt. For cobalt atomic number, how much in the sense 27. Cobalt atomic number 27, therefore electronic configuration is argon 3d7 4s2. In the complex, cobalt oxidation number is 3 plus, therefore electronic configuration is argon 3d6 4s0. Now we will take COF6 3 minus complex. Here valence shell D subshell is having D6. Here we will see T2G and EG. T2G and EG set we will see. Now 6 electrons, first electron here, second electron here, third electron here. Now we will see regarding the fourth electron. Where fourth electron will go, we will see. That means now you say delta naught is 13,000, pairing energy is 21,000. Delta naught is less, pairing energy is more. Delta naught is less than pairing energy. Delta naught is less means to go to EG, less energy required, but for going to pairing, more energy is required. Therefore, fourth electron will go to where you think? Fourth electron automatically go to EG. Fifth electron goes to EG. Then sixth electron. Sixth electron, where it will go? If it wants to go to this T2G, sixth electron, if it wants to go to T2G, it has to utilize, it has to take pairing energy from surrounding in order to repulsion with this. If sixth electron wants to go to EG, it has to take what energy? It has to take delta naught and it has to take pairing energy in order to repel with this. Therefore, we can say the sixth electron automatically goes to T2G, we can say. Now you see how many unpaired electrons are there. What is the configuration for this? T2G 4 EG2 is the configuration. How many unpaired electrons are there? 4 unpaired electrons are there in this complex. In this complex, 4 unpaired electrons are there. So experimental fact is explained, interpreted quantitatively by crystal field theory, but valency bond theory, did it explain like this? No. Valency bond theory did not interpret quantitatively. Okay. Now we will take CONH3 6 times 3 plus. This complex we will take. In this one, how it will be there, we'll see. Now CONH3 6 times 3 plus. In this one, D6 configuration is there. That D6 we will write. Now we will take T2G and EG we will take. We are taking T2G and EG. Here this contains 6 electrons, first, second, third. Now we have to talk about fourth electron. Now here, how delta naught and pairing energy are there, we'll see. Okay, delta naught is 23,000, pairing energy is 21,000 in the case of this complex. Okay, now fourth electron requires this much energy in order to go to EG. Fourth electron requires this much energy in order to pair. Which energy is less? Pairing energy is less. So fourth electron will go to where? For pairing in T2G, isn't it? Fifth electron also goes for pairing. Sixth electron also goes for pairing in T2G. Therefore, the configuration is what means T2G6, EG0. This complex electronic configuration is T2G6, EG0. We are saying. Now you say, is there any unpaired electrons in this? No. So in this complex, unpaired electrons not present. 0 unpaired electrons. So crystal field theory explained quantitatively this one. Okay. Therefore, now we can say here ligand is strong. Therefore, pairing takes place in T2G. Here ligand is weak. Therefore, without pairing, electrons going to EG. Okay. So why it is low spin? Why it is high spin? Have we got idea? Now you see that here ligand is strong. Ligand is forcing the electrons to go for pairing. Ligand is weak. Ligand is not forcing electrons to go for pairing. Therefore, it is high spin, it is low spin. It is inner orbital complex, it is outer orbital complex. In the crystal valency bond theory says that this hybridization is a D2sp3, inner orbital complex. This is a sp3d2, outer orbital complex, high spin complex. It is low spin complex, like this. Sorry, okay. So now we said based on crystal field theory, this octahedral complex we have explained. Even a tetrahedral complex also, how the crystal field splitting will be there in the tetrahedral complexes. How the crystal field splitting will be there in the tetrahedral complexes, that we will see. It is for octahedral complex. For tetrahedral complex, how it will be there? That point we have to see. In the tetrahedral complex, how the d orbitals will be getting split. For that case, first we will see how the tetrahedral arrangement will be there and how the ligands will be there. That we will see.